Alright, so in this video I would like to discuss the topic of a gradient field. Now, a gradient field is a special type of vector field that we can really express using the gradient operator that we learned a couple of units ago. A important thing that we remember is that the gradient vector provides on a level curve, it is perpendicular to the level curve, so it indicates the direction of highest magnitude, if that makes sense. That is perpendicular or normal to the level curve. So we don't need to waste too much time preluding this. Let's just get started. We define the gradient as a vector quantity. If I want to take the gradient using nabla f, then I get a vector quantity, and we call that vector quantity now a vector field f. So if I take the gradient of f, then I have a vector that is composed of all of the different first-order partial derivatives that one can take of f. So if I have n dimensions, if I have n variables of my function f, then I will end up getting a n-dimensional vector. So in the general case, the case that we use most likely, if I take the gradient of f, that's usually going to be the partial derivative with respect to x of f and the partial derivative with respect to y of f, right? So that should make sense. And of course, what this is a vector field, because this is a vector, and the derivative at all of these different points could be different. So if I take some xy, the partial derivative of f will be the x component of that vector, and the partial derivative with respect to y will be the y component of that vector, and then I'll have tons of vectors all over the place that will describe this gradient vector field. So why is this gradient vector field important? Well, we can define something very important with it, which is the idea of a conservative vector field. So this doesn't mean all that much to us right now, but it will shortly. And this says that vector fields are conservative if there is some function, some scalar function f, such that a vector field, capital F, can be modeled by the gradient of f. So given a scalar function, I can take its gradient and turn it into a vector field. And now the reverse process is called finding the potential function. So if I'm given f, then I need to reverse the gradient operator to find the scalar field. So to verify that some vector field is conservative, I need to reverse the gradient operator. Now, reversing the gradient operator is something that's a little bit finicky, because what you end up having is you have some function of x and y. Then you need to integrate this. You need to integrate this with respect to x. Then you also need to integrate it with respect to y. And then the constants that you get are, for f, you might get fx plus some function g of y, and then fy plus some function g of x. And you need to figure out what this function is, and you need to find out what that function is. And it turns out that if you can find one of them such that you found a scalar function such that its gradient is f, then it turns out that that's the only one you can get. There's a uniqueness theorem that exists that says that you found the right one. Okay, anyways, that's a bit of a digression. We'll look at finding potential functions a little bit later when it becomes more relevant to our work, but for now, let's try finding a gradient field and figuring out its geometrical meaning. This pretty picture down here is just the example that we'll be using, and you'll see why I put it there in a moment. Let's find the gradient field of the function f of x, y is equal to x squared y minus y cubed. The function that I graphed here is this function f of x and y. It's a very nice shape, and we're looking at it from the position of the z-axis. So the z-axis is pointing up and out of the blackboard. So we're looking at an xy, and then I could cut off these level curves that are kind of in red here, and then those would be the level curves on a two-dimensional plane. Anyways, let's find the gradient of this friend. So if I find the gradient of f, I get partial xf and then partial yf. Taking these partial derivatives take the partial derivative of this, because that's the only x-dependent quantity, 2xy, then y is dependent on both of these quantities. So for this, the y goes away, and for this, we reduce to 3y squared. So we found the gradient is 2xy, and x squared minus 3y squared. Now this is a vector field, and what this vector field models is that any given level curve, it finds the normal, so say I'm taking this level curve, it finds the normal vectors out there as a unit vector. And of course the magnitudes are going to be varying, but and then there will probably be some here. What is this? 1, 2, 3, 4. There'll be some over here. Then there'll be some more on the other side pointing back out as well. And remember, these are confined to 2 dimensions right here because we're concerning ourselves with one level curve of this. Anyways, that's the idea of a gradient field. In the next video, we will introduce line integrals and look at the fundamental theorem for line integrals, and we'll be bringing back the idea of a gradient field and, more importantly, the idea of a conservative vector field back into the mix. We'll see you then.